Hello everyone. Structured return types. We have a server that registers tools, returning structured data, and a client that calls them. The question we are answering, what does FastMCP do with the return type annotation? And when does the result contain usable structured data? First, part 1, the server. FastMCP registers the tools, BaseModel, TypedDict, and Dataclass are three of the structured return types demonstrated. The other two tools use plain classes with no special imports. Next, creating the server. One line creates the server. Every tool registered below belongs to this instance. Tool 1, get underscore nutrition. Pydantic base model. Think of this like a nutrition lookup, the kind a calorie tracking app or meal planner would use. Nutrition info is a pydantic base model. FastMCP introspects the field annotations to generate a full output schema with named typed fields. Base model is the most explicit pattern. Field names, types, and the schema contract are all declared in one place. Tool 2, get underscore cooking underscore time, TypedDict. Think of this as a time estimator, the kind a meal prep app would use before scheduling a dish. Cooking time is a TypedDict. At runtime, it's just a plain Python dictionary, no class instance. FastMCP reads the class level annotations the same way it reads base model fields, generating an identical output schema. The difference from base model is the ergonomic. TypedDict is lighter weight and natural when you're already working with dictionaries. Tool 3, get macro ratios, which is a dictionary. Think of this as a macro breakdown, ratios between 0 and 1, keyed by nutrient name. No name class is needed. The dictionary string float annotation is enough for FastMCP to generate a schema. But unlike BaseModel or TypedDict, it can only express values of floats. The specific keys, carbs, protein, fat, unknown until call time. So the schema uses additional properties, type of a number instead of named fields. You will see this in action exactly at invocation. Let's proceed with tool 4, get underscore dish underscore rating. Plain class with annotations. Think of this as a rating lookup, crowdsource and reviewer name as name fields. Dish rating is a plain Python class with class level annotations and a manual dunder in it. FastMCP calls get underscore type underscore hints on the class, finds the annotations, and generates a full output schema, the same as base model or TypedDict. Tool 5, get underscore substitute. Think of this as an ingredient substitution tool, original substitute and conversion ratio as named fields. Ingredient substitute is a data class. The decorator auto-generates dunder init from the class level annotations. No manual init needed. FastMCP uses those same annotations for schema generation, producing identical output schema to tool 4. And finally, tool 6, get underscore recipe underscore note. It's a plain class without annotations. Recipe note has no class level annotations. Dish and node only appear in init parameters. FastMCP doesn't inspect dunder init for schema generation, only class level annotations. With nothing to build from, no output schema is generated. You will see this in action at runtime, where we'll dig in deeper and understand this better. Next, starting the server. We can comment, uncomment to switch transports. With stdio, the client spawns the server as a subprocess. Run the client only. With streamable HTTP, start the server in one terminal, then run the client in another. Part 2, the client. Async IO and JSON are standard libraries. The client is async and dumps the tool response to JSON. OS and sys resolve the virtual environment's path. Client session manages the MCP session. stdio server parameters configures subprocess launch. Types provides text content, stdio underscore client, and streamable underscore HTTP underscore client are two separate transport options. One is commented out depending on which transport the server is running. Next, the setup. This builds the absolute path to the virtual environment's Python executable. Using the wrong interpreter means the server can't find MCP and fails on startup. Handles Windows versus Unix paths automatically. stdio server parameters is a data object that describes how to launch the server as a subprocess, which Python executable to use, and which file to run. This is only needed for stdio transport, where the client is responsible for spawning the server. When using streamable HTTP, the server is already running independently, and this object plays no role. Next, running it. First, opening the connection. These two lines are the only thing that changes between transports. Comment out one, uncomment the other, client session, initialize, and all prompt calls below stay identical regardless of which transport is active. With stdio underscore client uses server params to spawn the server as a subprocess and returns read-write streams connected to it. With streamable HTTP underscore client connects to the already running server by URL and returns read, write, and the third argument. This third value is session metadata. We discard it. Client session wraps whichever streams come in and handles the MCP protocol. Session.initialize performs the handshake. Next, list tools. What the server exposes. Let's first run the client and see this in action, how everything works. Everything runs as expected, and this should also have generated a JSON file. We can open that too. Before running the specific tools, we first ran list underscore tools, which shows the server contract. The key field, outputSchema present, means FastMCP generated a schema from the return type annotation. Structured content will be populated at call time. Null means no schema was generated. Structured content will be none. 5 tools have a schema. One doesn't. Get underscore recipe underscore nodes null is the early signal before making any call. That structured content will be none. Let's walk through to the tool underscore response JSON. Get underscore recipe underscore node has output schema null. Everything else has a schema. This is the early signal. Before making a single call, you already know structured content will be none for that tool. The return type annotation alone determines this. Next, get nutrition and get cooking time reduces identical schema shapes. They all have an input dish, and it has produced an identical schema with the type specified. One uses BaseModel, the other type dictionary. Both have named fields with explicit types under properties. From the schema alone, you can't tell which pattern was used in the server code. Next, get macro ratio has a fundamentally different schema shape. Compare it directly with get cooking time. Here, dictionary string float can only express values are floats. It cannot enumerate keys. The schema tells you the shape contract. The actual keys only appear when the tool is called with the real data. We'll see this when we invoke the tool. Next, let's jump onto the invocation. First, get underscore nutrition. Here, session.callTool sends the tool name and arguments to the server. The server runs the function, serializes the result, and returns it. Result has 2 fields. Content, which is a list of content items, typically text content carrying a JSON string. Structured content, a dictionary populated when the schema exists, none otherwise. Content is a JSON string, the wired representation. Reading from it means parsing JSON. Structured content is already a Python dictionary. Read it directly by key, no parsing needed. Both carry the same data. Structured content is the right layer to use in the code. Base model field names appear as dictionary keys exactly. Invocation 2, get cooking time. This has an identical wire behavior to base model. Same two layers, same JSON content. Type dictionary is a plain dictionary at runtime. The class level annotations are type hints only. FastMCP uses them the same way it uses base model fields. Next, invocation 3, get macro ratios. The key names carbs underscore percent, proteins underscore percent, fat underscore percent weren't in the schema. They only appear here. The schema, additional properties type number, describes the shape contract. Structured content carries the actual values built from the real data at call time, not from the schema. Tool 4, get dish rating. Structured content is fully populated. FastMCP reads the class level annotation via get underscore type underscore hints, builds the schema, and extracts the field values. Content is a memory address. Pydantic underscore core can't serialize a plain class instance. It falls back to string. This split is sharpest here. Valid output schema in list underscore tools, valid structured content at call time, useless content. When returning a plain annotated class, always read from structured content. Invocation 5, get underscore substitute. In this, both layers are populated. Add data class gives FastMCP annotations for the schema and makes the class natively serializable by Pydantic underscore core. Compare this with invocation 4. Dish rating and ingredient substitute have identical annotation. The only difference is at data class, the single decorator fixes content. Next, invocation 6. Get recipe note. Structured content none. No class level annotations. No schema. No structured data. Content is a memory address. Same Pydantic core, fallback as invocation 4. But here, there's no structured content to fall back either. Output schema is null in list tools, which was our early signal. We knew this was coming before making the call. In closing, two separate questions. Determine what you get back from a tool call. Will structured content be populated? FastMCP generates output schema from class level annotations. Base model, TypedDict, plain class with annotations. And add data class always qualifies. FastMCP finds the annotations and builds the schema. A class with annotations only in init parameters does not. Output schema is null and structured content is none at every call. You can see this before making any call from list underscore tools. Will content be usable JSON? Pydantic underscore code serializes base model, TypedDict, dictionary, and add data class natively in JSON. A plain class instance, even one with class level annotations, fall back to string, producing a memory address. Annotations determine the schema. They don't fix serialization. A data class fixes both. Switching between the transport is straightforward. All we have to do is comment out the transport from stdio and uncomment streamable HTTP. That takes care of the server. Let's run the server. The server has fired up. Now let's take care of the client. Let's comment out stdio client and uncomment streamable HTTP client. Let's open another terminal. Let's now invoke our client that speaks to the streamable HTTP server. Perfect. Everything works as expected. We covered a lot today. Now it's your turn. Run the code, rewatch it, break it, rebuild it. That's how you actually learn. Make it your own. Thank you.